So, good morning or good afternoon or good evening, everybody. So, this is the fourth module of our SAMOSAFER online school. Today, we will speak about the thermochemistry of the molten salt reactor. So, the first part of this module will be devoted to the basic lecture and interactive one. And then in a separate with a separate link, you will join the webinar part of this module, which will start at 5 p.m. But going back of today and the topics of this lecture, the first speaker of today is Sylvie Del Pesce. She is a researcher, a CNRS researcher at Institut de Physique Nucléaire d'Orsay in the radiochemistry group, and it's the research topic. It's the chemistry actually of the molten salt. So, Sylvie, I give you the floor.
Thank you, Stefano, for this introduction. Is it okay? Do you see my screen?
Yeah, if you go to the full screen mode, perfect. Yeah.
Okay. So thank you, Stefano. So good afternoon, everybody. So today I am to do this small introduction to molten salt reactor thermochemistry. And I will present briefly during this presentation our analytical approach to understand the chemistry of a molten salt and also the chemistry of solutes in this molten salt. So it's very important to know the chemistry of salt and solute in the molten salt, because by this way it will be possible to determine the oxidation states of the solutes in a given molten salt, and then to deduce the physical state of these solutes. So it is important in molten salt, for the molten salt reactor application, to know if the elements which are produced in the reactor core are on the gas state, soluble, are they solid, for example, with precipitation of oxide, or are they produced under their metallic state? This knowledge leads also to propose ways for extraction and separation of elements in the reprocessing, and also to assess the corrosion resistance of structural materials. So how to do that? We generally we do the construction of potential acidity diagrams. So in this presentation, I will focus on the three main questions. What are these diagrams? How to build them? And what are their limitations? So first, what is the oxoacidity? So we talk about potential acidity diagram, but how can we define the oxoacidity? In the case of fluoride and chloride salt, we can talk about fluoroacidity and chloroacidity, but in this case, it is we will focus on the oxoacidity, and the oxoacidity was defined by Lux and Flood, and it is related to the presence of the oxide ion in the molten salt. And finally, we define the oxoacidity by this function. It is PaO2 minus, and it is equal to the opposite of the logarithm of the activity of oxide in the salt. You have to know that in the molten salt, in all the salts, we have oxides. So oxides came from water or air, and we have oxide in all the salts. So we have to consider this presence in our salt. And generally, the activity of the oxide is not known, and to do some calculations, we have to consider pure compounds, and generally we consider lithium oxide, if obviously lithium chloride or lithium fluoride is present in the salt. In the case of sodium chloride salt, we will consider the activity of sodium oxide. Okay, so that is a potential acidity diagram, it's typical. So in the y-axis, you have the potential. In the x-axis, you have the function PO2 minus. And the objective in this diagram is the distribution of stability domain of several compounds. For example, here it is nickel, which was calculated. The diagram of nickel was calculated, and we observe in the green the stability domain of metallic nickel, in blue the domain of stability of nickel 2+, and here in red the stability domain of nickel oxide. So we are limited here by the oxidation of chlorides ions to chlorine gas, and here by the reduction of sodium plus to sodium metal, because we are in a sodium chloride molten salt. So we can compare these kind of diagrams to the classical diagrams of Pourbet, which were constructed by Pourbet for aqueous solutions. And we see on this diagram, in the left of the slide, the diagram of iron in aqueous solution. So the aqueous solution stability, the water stability, is represented on this diagram by the zone colored in blue, the blue zone. And what we observe that we have no intersection between, for example, the stability domain of iron, which is there, with the stability domain of water. That means that iron is not stable in water. Iron can exist in water, but under higher oxidation state, 2, 2 and 3, and 3, but never at its metallic state. Here on the right side, we have the potential acidity diagram realized for iron in lithium chloride, potassium chloride salt. In this case, we observe a very large domain of stability of iron at its metallic state. So we see that between these two, the thermodynamic data are exactly the same, but we see that the chemistry of iron will be strongly dependent on its environment. So how to build this kind of diagrams? First, we have to determine what are the limits of the solvent. For example, we are going to work with this solvent, lithium potassium chloride, which is a very well-known molten salt. And we are going to define first the redox or electroactivity limit of this salt. The anodic limit. We have only one compound which can be oxidized in this salt. It is the chloride anions Cl-, which can be oxidized to chlorine gas. That is the only reaction which can be occur in anodic side. In the cathodic side, we have two options because we have two metallic cations. We have lithium plus and K plus, potassium and lithium. So we can be limited by the reduction of lithium plus or potassium plus. To know that, we have to calculate what are their reduction potential. So we are going to write the reaction of reduction, the electrochemical reduction of lithium plus to lithium metal. We cannot have a potential without a reference potential. So we are going to choose as a reference potential the chlorine gas evolution. That will be our reference reaction. So we are going to write the Nernst relation, and In the same time, we are going to write this reaction, which is the sum of these two half reactions. So this reaction, from this reaction, we can calculate its constant equilibrium constant K, and K is calculated using the Gibbs energy, and by this relation, and we can calculate delta G using the thermodynamic database of pure compounds. When we are at this equilibrium, that means that we have the two potentials which are equal. So we are going to do equality of these two relations, and then we can write this relation in which it will appear the constant equilibrium K. And then we observe that we have a direct relation between the standard potential of lithium, so the relation of the standard potential of lithium and the Gibbs energy. So it is possible to calculate this value. Then after, we are going to use this relation to determine the potential of lithium against the chlorine gas. And we have this relation, which are really easy. So in this relation, just to mention that we have the activity of lithium chloride. In our case, we will consider that the activity is equal to its mole fraction. So in here, it is 0.588. And we will come back on this point later. So just one remark. Generally, we consider that alkaline chloride and fluoride are totally dissociated, so that we have a dissociation total of anions and cations in the salt. And then in this case, because we have no relation, no complexation reaction in the salt, we are going to consider that the activity of chloride or activity of fluoride are equal to 1. But in the case of molten salts containing alkaline earths or other salts, that is the case with calcium, thorium, aluminium, for example, the solvation of the salt by the fluoride, or it's the same with chloride. So we have, for example, here, thorium fluoride can be solvated by fluorides to produce these very big complexes with a lot of fluorides. That leads to an activity of fluoride or chloride which is not equal to 1. And in this case, we are going to do a very approximative calculation of the potential acidity diagrams. So we will consider that these activities are equal to 1 as a first approximation, but after, a correction will be done after only experimental measurements. So we have calculated the potential of lithium, and in the same way, we can do the same calculation for the potassium. So for the potassium, we have this relation. It's the same than for lithium, but obviously the Gibbs energy is not the same here, and the activities here are not the same because we are going to take the mole fraction. So when we do the calculation, we obtain these values of potential, and then the limit, we observe that the potential of lithium chloride is higher than the potential of reduction of potassium chloride. Then the cathodic limit in lithium potassium eutectic molten salt is the reduction of lithium chloride. One question also, in the vertical axis, what is the limit? In this case, we can calculate that lithium oxide is more stable than potassium oxide, so it will produce before. Then the limitation in the vertical line in the x-axis will be the formation of lithium oxide. Another point which has to be considered for the construction of these diagrams is the oxidation of the oxide to oxygen. So in the same way, we have always the same approach. So we write the electrochemical reaction, we write the Nernst relation, we have the global, the chemical reaction considering as a reference the chlorine gas evolution. And using this chemical reaction, we can deduce from the Gibbs energy the value of the standard potential, which is introduced in this relation. So in this relation, we have the relation between the potential of oxygen as a function of the activity of lithium oxide, that is the x-axis, that is the y-axis. And then we have all the other data. The activity of lithium chloride is considered equal to its mole fraction. The activity of chloride ions is considered equal to 1. And the value of the vapor pressure of oxygen is introduced as we want. We have to put 1 atmosphere or 10 to minus 1, 10 to minus 2 as you want. So finally, we have this diagram, which is the stability domain of lithium potassium chloride. Here we have the oxidation of chlorides to chlorine gas. Here the reduction of lithium chloride to lithium metal. This limit here is the oxidation of oxide to oxygen. And here, I have forgotten to put it in green, but here we have the precipitation of lithium oxide. Now we can do the same for a fluoride molten salt, and I take this example, lithium thorium fluoride molten salt, because it is the salt retained for the molten salt fast reactor concept. So what are the redox limits? Anodic limit, the same than in chloride salt. Now we have fluoride ions. It is the only ions which can be oxidized. So we write this electrochemical reaction with the fluorine evolution. In the cathodic limit, we can reduce two cations, lithium and thorium. So we are going to write the electrochemical reaction, the chemical reaction, the Nernst relation in the two cases, and calculate, using the thermodynamical data of pure compounds, the Gibbs energy. And then from the Gibbs energy, we can deduce the potential of reduction of thorium and lithium. In this case, we observe that the potential of thorium is higher than the potential of lithium, then the cathodic limit will correspond to the reduction of thorium-4. Like in chloride salt, we have to look at the oxidation of oxide to oxygen, and then we do exactly the same as previously, and we have this relation which give the variation of the potential of oxygen evolution as a function of the cologarithm of activity of lithium oxide. We observe that the standard potential is calculated from the Gibbs energy. The activity of lithium fluoride is taking equal to its mole fraction. And then we can draw the variation of this potential as a function of the activity of lithium oxide. We have also to determine the acido-basic limit. So the vertical line represents the activity of lithium oxide for which we have the precipitation of thorium oxide. Then to determine this activity of lithium oxide, we have to write this equilibrium. There is no modification in this equilibrium of the oxidation state, but thorium fluoride will be transformed to thorium oxide. So with this reaction, we can calculate using pure compounds data the Gibbs energy and deduce the value of this equilibrium. And this constant K the equilibrium constant K is described by this relation in which the activity of thorium oxide is taken equal to 1. We consider that the thorium oxide is on the precipitate form, and so it is a solid, and then its activity is equal to 1. The activity of lithium fluoride and the activity of thorium fluoride are given by their mole fraction in this molten salt composition. And then the constant K has been calculated from the Gibbs energy. Then we can deduce that we have precipitation of thorium oxide when the activity, the opposite of logarithm of activity of lithium oxide is equal to this value. Then now we can do the construction of our stability domain of our salt. So here we have the fluorine gas evolution. Here the oxidation of oxide to oxygen. At the cathodic limit corresponds to the reduction of thorium-4 to thorium metal. And here we have the precipitation of thorium oxide. So by this way, we have defined the limits of stability of this molten salt. So now, that is very good, but what can we do with that? So we are going now to superimpose to this diagram the diagram obtained for other elements. For example, for uranium. So we did the same calculation for uranium, and we superimpose the limit of our solvent, lithium thorium fluoride. And we have to consider only what's happened in the limit defined by our solvent. And we observe, in the case of uranium, that we have two soluble species, uranium-3, uranium-4. We have at the very high potential values a domain of stability for UF6, which is on the gaseous state. We observe that uranium metal is very close to the limit of reduction of thorium. We have also two very small domains here of stability of oxide, oxyfluoride here, and the oxide U308 here. So just a remark. Experimentally, we did a lot of experiments in the lithium thorium fluoride salt, and we observed clearly the reduction of UF3 to uranium metal. So that means that these diagrams are very interesting, but they can be modified because we did to calculate these diagrams, we did a lot of approximation and assessment. But so first, we didn't consider the solvation effect of the element. So generally, the activity of one element is given by the product of its mole fraction and its activity coefficient. And that is very important because that will change the position of the redox potential. Another point is to consider an activity of fluoride ions which is equal to 1. That is very possible to do that when we have alkaline salt, but when we have more complex salt, it is the case of lithium fluoride, thorium fluoride, because we have seen that thorium fluoride can have a lot of fluoride ions against around him. So it's not very good to consider that the activity of fluoride in this case is equal to 1, and that has to be improved. So how to use these diagrams now? For example, for reprocessing, I present here two diagrams. One in the right side was calculated for neodymium fluoride. It is always in lithium thorium fluoride salt. And in the left side, it is calculated for neptunium. So we see that neptunium is very more complicated than neodymium. So can we perform the separation between these two elements, and how can we do that? So first we have to describe what we have. What we have for neodymium, we have only one soluble species, it is NDF3. No other elements which are stable in all the domain of stability of our solvent. In the case of neptunium, it's more difficult, there are more options. Two soluble species, NPF3 and NPF4, and for the very high potential values, two gaseous forms, NPF5 and NPF6. We can see also at the lower potential values the possibility to do the reduction of NPF3 to NP metal. So we can do its reduction by electrolysis, for example. And we have also here a very small domain with NPO2, so we can do the precipitation of neptunium oxide. So to do the separation between these two elements which could be present in the same molten salt, lithium thorium fluoride, we have three options. The first one is to apply a high potential value, or to do a bubbling of a very oxidizing gas like fluorine gas. So if we do fluorination, or if we apply a very high potential value in the molten salt, in this case, we will oxidize neptunium to its highest oxidation state. It will be on the gaseous form, and at this moment, it will be separated from the molten salt, and it will be in the vapor phase behind the salt. And nothing will happen for neodymium when we increase here the potential. So that is the first option. Second option, we can apply a very low potential value. For example, we can do electrolysis and remove neptunium on a solid cathode, and neodymium won't be reduced in the same time. So we will have a separation of the two elements. We can also use a reductant species like lithium, which is very high reductant species, which can be dissolved in bismuth, that is typically a reductive extraction, and then we can remove neptunium selectively with a high selectivity compared with neodymium. The third option is to be able to control both the potential and the acidity. For example, if I can control the potential here and acidity at this point, where is the laser point, at this moment we are going to precipitate neptunium oxide selectively, because at the same point here, neodymium is always on the soluble form. And we can, to do that, we can use a gas mixture which is composed of hydrogen, HF, and water. And in this case, if we introduce and do bubbling of this gas mixture with the very good composition, we can do the precipitation, selective precipitation of neptunium oxide. So to use a gas mixture, we have to write these classical equations, and we can deduce from these equations the ratio of the vapor pressure of all the gases, and with the Gibbs energy determine the standard potential which are required here for this reaction. So the reduction of HF to hydrogen, or the equilibrium constant of the equilibrium between water and HF. And in this case, we can deduce a composition which is interesting, which is of interest to apply one potential and one oxoacidity. Another application concerns the corrosion. So I present on this slide several potential acidity diagrams which were calculated for nickel, iron, chromium, tungsten, and molybdenum. And in yellow, we have a yellow band here. And this yellow band represents the stability domain of lithium fluoride, beryllium fluoride salt, which was a salt written by Oak Ridge National Laboratory for the MSRE and MSBR reactor concept. And the difference in the potential level corresponds to the ratio, the ratio uranium-4 over uranium-3, which is equal to 10 at the bottom of the yellow band and equal to 100 at the top of the yellow band. The American researchers have shown that they can control the redox potential of the salt using the ratio UF4 over UF3 by this using the Nernst relation. So they have shown that it was very interesting to use UF4 and UF3 in order to control the redox potential. And then they have shown that when the ratio is equal to 10, it's very interesting. And we see that when the ratio is equal to 10, nickel is not oxidized, iron is not oxidized, chromium, it's the limit of its oxidation, and it's okay for tungsten and molybdenum. But when the ratio increases to 100, we observe that we have oxidation of iron, chromium, and molybdenum. So we can control the redox potential using this ratio, considering these two soluble species. The limit at the acido-basic limit here is corresponds to the precipitation of uranium oxide. So we observe that in this kind of salt, so lithium, beryllium, uranium fluoride salt, the stability domain of the salt is very, very short. We have only this yellow band, and all the elements will be in this band. So, for example, here chromium will only be on the chromium fluoride 2 form. So it's very short stability diagram. So some comments about what I presented before. So these thermodynamic diagrams give a lot of data on the chemistry of the solute for a given molten salt. So we have a very good idea of the oxidation states which are possible, and then the physical states of the elements, their reactivity in terms of corrosion. Each molten salt has its own properties, so the diagrams have to be constructed for each salt. Each salt has its own redox potential, which controls the state of all the solutes in the salt. But this redox potential can be controlled using a soluble-soluble redox system, or also by a gas mixture, but that will be, I think, more difficult in the frame of a nuclear reactor. The potentials and the acido-basic limits are calculated using thermodynamic data of pure compounds without taking account of the solvation properties. But these solvation properties are obviously very important. And the solvation properties can be determined by experimental measurements. So what is the influence of solvation on the redox potential? So we have shown how to calculate the standard potential using thermodynamic and Gibbs energy. So we have this potential, which is calculated from Gibbs energy. And if we have a solvation on the oxidant element, in this case, we will observe a shift of this potential to the lowest potential value. So we will show an increase of the stability domain of the oxidant. And that was expected because if the element is solvated by the molten salt is stabilized by the molten salt. Then its stability domain will be increased. It will be the same for the reductant. If we have a solvation on the reductant species, in this case, we will observe an increase of its stability domain and then an increase of the redox potential. And we can express the difference of potential due to the solvation by this relation in which the term in gamma red and gamma ox are the activity coefficients. And I recall here the relation between the activity coefficients, the mole fraction, and the activity of the elements. So the solvations on the oxidant depend on the molten salt properties, and the solvation on the reductant can depend on the molten salt properties if the reductant is a soluble element. But if the reductant is, for instance, a metallic element, in this case, we can use this particularity, the solvation on the reductant element. We can use that to do a reductive extraction using a liquid metal. So, about the reductive extraction, we use a metallic solvent, which is bismuth generally, in contact with the molten salt. And in bismuth, we introduce lithium, and lithium is a very big reductant species. And if the concentration of lithium is, we have to choose this concentration of lithium in order to control the redox potential here at the interface between the liquid metal and the molten salt. And we will reduce the elements, some elements which are in the molten salt in this way. And that is, okay, I've forgotten this slide. So we have, that is a slide which came from the Oak Ridge National Laboratory. They did a lot of reductive extraction using bismuth, and they have determined by experiment, by their experiments, the logarithm of the distribution coefficient. And the distribution coefficient is given by this relation. It is the distribution of the element M between the liquid metal here over the molten salt here. So they did experimental measurements, and they have these results here, which are represented here by this line, the solid line. And in the same time, they did some calculations. So we can express this distribution coefficient as a function of thermodynamic parameters and solvation parameters. So after they did the calculation, considering that all the activity coefficients are equal to 1, and in this case, they calculate this curve, which is very far from the curve obtained by experimental results, by experiments. Sorry. After, they consider only the activity coefficients of the elements in the liquid metal. So that was determined by Lebedev, and so these data are known, and then they consider only that the activity coefficients in the molten salt are equal to 1. So only considering the activity coefficients in the liquid metal, they obtain this curve, the dashed line here, and we observe that it's very close to the experiment results. Then they conclude that in their case, in lithium beryllium fluoride salt, the activity coefficients of these solutes are close to 1. And that is possible because beryllium fluoride is one of the most acidic salts. So beryllium fluoride will take a lot of fluorides around him, and then the activity of the solute in the molten salts are not there is not a lot of solvation of these elements, and then their activity coefficients are close to 1. But that is very specific of this molten salt. So when we calculate the potential of the elements, both on a cathodic, without considering a liquid metal and considering a liquid metal, we observe that the redox potential are very different. So here, without liquid metal, we observe here the limit of the reduction of thorium fluoride to thorium metal, and we see that we have the reduction of actinides in the right side of this electroactivity limit. And the lanthanides are over this limit, and then they cannot be reduced in the molten salt. But when we look at this redox potential in a bismuth liquid metal, in this case, we observe a strong shift of all this potential to the highest value that is due to the solvation effect on the reductant element. And in this case, we can consider the possibility to do reductive extraction of both actinides and lanthanides in lithium thorium fluoride salt. Just a comment about lithium fluoride, thorium fluoride salt. So we did some experimental studies of zirconium in this molten salt, and we have constructed, we have built the potential acidity diagrams of zirconium in lithium thorium fluoride salt, and using only thermodynamic data of pure compounds, and we observed a domain, a stability domain of zirconium fluoride 2, and then we have these diagrams. And here on the left, on the right side, sorry, you have the experimental diagram. So we observe that zirconium fluoride 2 is not stable. We didn't observe the formation of this oxidation state. And another point, we observe that the limit of the thorium fluoride salt are not the same than the limits calculated using thermodynamical data. And what we observe that is very strange, because we can think that thorium fluoride will be solvated by fluoride ions. So we will have an increase of this diagram. So we expected a decrease of this potential in order to increase the stability domain of thorium fluoride. But in fact, we observe a decrease of this domain of stability. So that is due to the influence of the activity of fluoride ions. So if we look at this reaction of thorium fluoride, we observe that in this reaction and in the Nernst relation, we have the activity of fluoride ions which involved in this reaction. And we have a power of 4 here. So if the activity of fluoride ions is not equal to 1, but lower than 1, in this case, the experimental potential will be higher than the thermodynamic potential. And it's the same when we look at the limit oxoacido-basic, this limit here. When we write the constant K, we observe that it depends on the logarithm of activity of fluoride ions. I have formatted the 4 here. And if the activity of fluoride is lower than 1, in this case, the limit will be shifted to the highest values of Pa of lithium oxide. So in lithium thorium fluoride, the influence of the activity of fluoride is higher than the influence of the solvation on thorium fluoride, even if the thorium, the solvation on thorium fluoride will be also very important. So to conclude, The construction of potential oxoacidity diagrams from a thermodynamic database of pure compounds give many data about the stability domain of a molten salt, its redox behavior. We know what are the reactions will limit the cathodic and the cathodic side and so on, and the stability of solute in the molten salt and their possible oxidation states. When we know the oxidation states, we have a very good idea of the physical state of the elements. We have seen that the comparison of diagrams leads to proposed separation processes, and also we can predict the corrosion behavior of structural materials. Experimental measurements lead obviously to improve the diagrams, considering first the solvation effects, the activity of fluorides or chloride ions in the molten salt when the chloride and fluorides are not totally dissociated, and experimental measurements are very important to know also the redox potential of the salt, and then to know at what value of potential we can expect to be. So thank you for your attention.
Stefano, could you please verify that you can see my screen, please?
I can see your screen in full screen mode.
Excellent, thank you. And it also looks like we're right on time, so good job keeping this in order. Okay, greetings everyone from Canada today. Good morning, good afternoon, good evening. My name is Marcus Pirro. Thank you, Stefano, for the nice introduction. I'd like to also point out that Max Pochman and Nicholas Skuro from our group at Ontario Tech have provided contributions to this presentation as well. So I'll be giving a lecture today on computational thermodynamics with the focus on thermochemical software for the 4th module of the SAMOSAFER Summer School. First, I'd like to acknowledge Dr. Andrew Benes and Elisa Capelli for some very nice technical discussions on the JRC molten salt thermodynamic database, and also other members of the SAMOSAFER group for technical discussions more broadly to MSR behaviors, and also the Canadian Research Chairs Program, the Natural Sciences and Engineering Research Council of Canada that has funded much of this work. A quick outline of what I'll be speaking about today. I'll be giving an introduction to computational thermodynamics, brief theory of Gibbs energy minimization and models, equilibrium point calculations, and various case studies. So first, a brief introduction to computational thermodynamics, as I appreciate a number of folks on the line may not be subject matter experts, and I'm hopeful that this lecture today can give a good first introduction to this topic. I also realize that there's some persons that may be fairly familiar with CalFAT and computational thermodynamics. I hope that parts of this lecture would also be useful to them. So first, what can you do with computational thermodynamics? Well, you can use it to perform a number of different types of calculations, including phase equilibrium, including speciation. So for example, under what kind of conditions could you expect things like precipitation forming, different phases, phase transformations taking place, what's the speciation of those different phases, and so forth. Phase transformations could include, for example, looking at steels, whether you're dealing with ferrite steels or martensite, or if you're dealing with salts, if you're dealing with trying to predict melting behaviors or vaporization. Similarly, one can compute driving forces of metastable phases, various thermodynamic material properties like enthalpy and heat capacity, and also to generate phase diagrams. So to give a very brief set of examples, on slide 7 we have an example of the uranium-oxygen phase diagram from Christine Guinaud and her colleagues, and the phase diagram you see here on the screen was generated by thermocalc using multiple sets of thermodynamic models. And as you can see, those models used together to compute this phase diagram reproduces quite well available experimental data. So with these tools, one example of what you can do is you can tailor the phase diagram to look at conditions that may be of interest to a particular application. So simple examples could even just be looking at different bounds of the system, looking at different pressures and such. The figure on the right gives a bit more of a detailed example of a point calculation. This was using a different database from the Royal Military College of Canada that is representative of irradiated CANDU fuel at 2000 degrees Kelvin. And for this particular fuel, which is typical burnup for CANDU fuel, fairly low for LWR fuel. But what you can do here is you can see, and I'll just use my pen here, you have, this is written in the fact stage output. You have these different blocks here corresponding to different phases. And so the first one I've outlined here is the gas phase, where we see that the number of moles of the phase is written here in this format, followed by the mole fractions of different species within the gas. Xenon is predicted to be the most dominant in this case, not surprising at all. Then followed by the fluorite UO2 solid solution phase with various dissolved fission products. And you can see here the total quantity of the fluorite phase, in addition to various species that are predicted within it. UO2 is the most dominant in this case, followed by plutonium and various other fission products species. Noble metals follow. This is commonly referred to as the white phase with the hexagonal close packed crystal structure and so forth. So anyways, I hope this gives a bit of an idea of what kind of calculations that you can apply with these thermodynamic tools using UO2 as a reference. Thermodynamic equilibrium is computed in these cases, which really rely on 4 conditions. 1 is the Gibbs phase rule, 2 is conservation of mass, 3 is conservation of energy, which is really the first law of thermodynamics, and 4 is that the entropy of the universe tends to a maximum, which falls under the second law of thermodynamics. Combining the 3rd and 4th conditions is equivalent to stating that the Gibbs energy of a system under isothermal isobaric conditions is at a minimum, is a more convenient way to numerically compute the problem. As a quick reminder of fundamentals of thermodynamics, the phase rule is written here, where F is the number of degrees of freedom, C is the number of system components, not necessarily equivalent to the chemical elements. Phi is the number of stable phases that are predicted to be stable. 2 is corresponds to the thermodynamic potentials of temperature and pressure that can vary. And finally, psi is the number of additional constraints that may be applied to the system, such as electrical neutrality, if you're dealing with an electrochemical system. And the Gibbs phase rule quite simply requires that F be non-negative. The Gibbs energy functions of the system can be partitioned using the equation given here, where the first term corresponds to solution phases, whereas the second term corresponds to stoichiometric phases. There's more than one way to represent the Gibbs energy of a system. This is just simply one convenient way by partitioning the stoichiometric phases from the solution phases, where the subscript lambda corresponds to the solution phase index. Expanding the Gibbs energy of the molar Gibbs energy of a solution phase can be written by the equation given here, where we have a combination of the reference Gibbs energies of the pure species, the ideal mixing of the species within that phase corresponding to the mole fractions, and finally the excess Gibbs energy. This really applies to a single lattice phase. Now the complication comes where the excess Gibbs energy of that phase is handled, which can be highly nonlinear and non-convex. That's where nonlinear optimization is required, in addition to global optimization techniques to handle the non-convexity of these Gibbs energy topologies. The most standard way to solve this problem is called Gibbs energy minimization, which is a numerical optimization technique that relies on a second series Taylor expansion of the Lagrangian function, which is given here. L is the integral Gibbs energy of the system minus your constraint function, which is gamma phi, which is basically the residual of your your mass balance equations multiplied by the element potential vector. And by solving this optimization problem, one can determine a unique set of number of moles of species and phases that yields a minimum of the Gibbs energy function while respecting the phase rule and mass conservation equations. So that's, obviously very mathematical. A very simplified graphical interpretation of what I just said is shown on slide 12. So if you were to imagine on the far left here, I have a generic phase diagram of some, let's say, solid and liquid region, where the composition between A and B is shown on the horizontal axis, the temperature is shown on the vertical axis. Now, let's say if we were to look at a particular temperature shown by this red dotted line, and then plot the molar Gibbs energy shown on the middle of the screen, and plot the molar Gibbs energy of the solid and liquid phases in this particular arbitrary example, one can draw a tangent line between the two phases, as shown in the main figure on slide 12. The tangent line between those two molar Gibbs energy curves corresponds to the equilibrium state. Now, the overall composition of the system, as represented by this vertical dashed line, can be used as a graphical means of determining the relative proportions of the solid and liquid phases. That's given by the lever rule. So in this case here, the points of tangency, so here we have the solid and here we have the liquid, that corresponds to unique compositions of both solid and liquid phases and the Gibbs energies of those respectively. Then one can compute, let's say, the Gibbs energy of the system using this type of equation. Obviously, I'm greatly oversimplifying the problem here, but this is just a simple graphical interpretation to what's going on in Gibbs energy minimization. Again, I'm greatly simplifying it. But one very important concept that is worth noting here is that this tangent line has, one can extract a lot of useful information from this tangent line, and that being that the chemical potentials of all species and phases that are predicted to be stable are effectively defined by this line. So that means that the chemical potentials of the solid solution phase is represented by this point here. Similarly, if this was represented by, let's say, species A within S and then species B within S, that the chemical potential of species A within S lies on that line. Similarly, the chemical potential of B within S lies on that line. Similarly, the overall molar Gibbs energy of the system is represented by the tangent line the point where the tangent line intersects the composition line, and a lot of other useful things. Similarly, lastly, the chemical potentials of pure A as a component of the system is represented by the extremum of A. Similarly, the chemical potential of system component B is represented by the point D on the other side. Now, one requires models in order to capture the Gibbs energies of these different phases, which may be various types of solids, liquids, and may have certain types of crystalline structures. They most likely have some departures from ideal behavior. The method in which those models are derived is called the CalFAD method, which has been very well established, including textbooks dedicated to the topic, an annual conference, a journal as well, and it's pretty well established. And the CalFAD method itself is effectively a methodical approach to derive these thermodynamic models, primarily from experimental data. So that is to say that these thermodynamic models are empirical by nature. You derive these models using experimental data as input. One of those models that is particularly well suited for molten salts, which is again the topic of the SAMOSAFER group, is called the modified quasi-chemical model. This model is particularly useful for short-range ordering in solids and liquids, particularly salts, and has been widely used to represent salts for molten salt reactors. It typically has two sublattices, and what's noteworthy is that at this stage, only FactSage and Thermochemica are the only thermodynamic software currently capable of handling this model. The modified classic chemical model was initially developed by the FactSage group. One of the distinguishing features of this model is that instead of focusing attention on the mixing of individual species or the mixing of constituents, let's say on a particular sublattice, the focus is instead on the mixing of pairs of species or quadruplets, not the species themselves. And that can be represented here. Let's say if you have a salt of A and B, in this case, what you're focusing on is the mixing not so much of A and B, but AA and BB pairs interacting with one another. Now, when you deal with a more sophisticated two sublattice model, where you have constituents on both cationic and anionic sublattices, you can have many more combinations where you may no longer have pairs, but now you may have quadruplets. So in this case, you may have A and B interacting, let's say, on the primary sublattice and X and Y on the second sublattice, and many mixtures therein. I'd like to point out, if anyone is interested in further details of this particular model, from a theoretical perspective, I'd recommend checking out the book that's listed at the bottom of slide 17. So there's a number of assumptions and limitations that are applied in this form of modeling, as is the case with every form of modeling simulation used in any type of engineering or scientific analysis. The primary assumption that's made in computational thermodynamics is that the conditions apply at thermodynamic equilibrium. Now, what I mean by thermodynamic equilibrium, I think that what is worth remembering is that the models themselves are empirically based, which means that the models are derived directly from experiments. So as an example of what I mean by an experiment, that may include, for example, powder of uranium dioxide that is then exposed to an oxidizing environment with a well-controlled oxygen potential and a well-controlled temperature, whereby the mass of that uranium dioxide powder is carefully measured, and more specifically, how much that mass has gained. So the condition of assuming thermodynamic equilibrium, again, is closely related to the experiments in which they are derived. So that is to say the equilibrium that is observed, let's say, with uranium dioxide powder. Again, that's one example. The same could be applied to various salt powders. So this experience in the field of computational thermodynamics applied to nuclear fuels has shown that the assumption is generally more reasonable and more appropriate at elevated temperatures and also with fluids rather than solids. That's not to say that the assumption is invalid for solid materials. It's just to say that it is a better approximation for fluids, both gases and liquids. And part of the reason for that is simply if you have a large, let's say, uranium dioxide pellet, the diffusion of particular components can be an important kinetic limiting factor. So having said that, one could argue that the assumption is more appropriate for molten salt reactors than it is for light water reactors. Now, what's also worth noting is that there are no extensive measurements or models of the chemical kinetics of nuclear fuels, especially with fission products. And also that a number of light water reactor and heavy water reactor fuel safety codes rely on this assumption to support safety and licensing. So again, that's not to say that the assumption is a perfect one, but experience has shown that this has been a reasonable approximation within error bounds. So what I'd like to do is, before moving on to more salt-specific applications, just to give appropriate context, is to give a case study of the appropriateness of assuming equilibrium thermodynamics, and to avoid appearing like overly critical towards others. I want to beat up on my own work. So what you're looking at on slide 19 is an analysis I performed about a decade ago in high burn-up PWR fuel. And what you're looking at on the left figure is the predicted distribution of phases across the radial direction at end of life in in very high burnup PWR fuel. It's about 100 gigawatt days per ton fuel. It's pretty high burnup. Now, what's noteworthy here is that great. So we see this fuel that's been irradiated. The models were directly compared to post-radiation examination experiments that were conducted at the Joint Research Center in Karlsruhe, Germany. And what's noteworthy is that both in those specific experiments and consistent trends that have been observed in UO2 fuel is that you generally only see 3 phases, with some exceptions of a few others. You really only see your fluoride, you see your gas, and you see the noble metal hexagon close packed phase. I mean, sometimes you might see some evidence of perovskites and perhaps something else, but that's kind of rare. We're under different conditions, like for fast reactors with MOX fuel. But you can notice that the models predict a number of other phases to precipitate in this fuel, and that is not experimentally observed. So that's one area where the assumption of equilibrium thermodynamics kind of breaks down. But what's also worth noting is that the same predictions agree fairly well with other experimentally measured values, such as the relative oxygen potential in the fuel, as shown on the right figure from the same set of predictions with measurements performed at JRC. And ultimately, what's worth noting is that the error bars are still pretty large, and that's no criticism of the experiments. It's just, irradiated fuel is incredibly complicated. So here's an example of where assuming equilibrium may not be that bad, but at least here we have some experiments to bound our levels of expectations. Okay, so I'm going to switch gears here to be specific to thermochemica, and which is the focus of this this school here. I'd like to acknowledge that there are several thermodynamic software packages in both commercial and open source domains. Some of the popular commercial software packages include FactSage, Thermocalc, and Pandat. These are all very good. I've never used Pandat, but I've used FactSage and Thermocalc, and I can say that they're excellent pieces of software with a number of great capabilities and documentation. There's also several open source tools, OpenCalFad, PyCalFad, and Thermochemica. Folks in our group have used OpenCalFad for a number of applications, which has worked out well. We haven't used PyCalFad directly, but our group has worked with the PyCalFad group. Now, this particular lecture is focusing on Thermochemica, not to exclude these other software tools, but just because that's the tool we're using for the SAMOSAFER work package 2. So please note there are some very good other tools available out there. A quick introduction to Thermochemica. It's an open source thermodynamic software library. It began during my PhD in 2008 and has became open source around 2013 with continuous development in capabilities and maintenance over the years. And the primary motivation for the software was really for direct coupling to nuclear fuel codes. And that is very different than conventional thermodynamic tools. Most conventional thermodynamic tools were intended for a user sitting in front of a computer and actively working with the software to do things like point calculations, generate phase diagrams or Poiret diagrams, or develop thermodynamic models. It's very different than when you start putting that into, let's say, a fuel performance code, where instead of calling it a handful of times, now you might be calling it billions of times. So it puts the emphasis on a bit of a different area. So I think that's worth keeping in mind. So the focus and the emphasis of the work has been on reliability, computational performance, and capabilities. So what I mean by that is, imagine you're calling a Gibbs engine minimizer a billion times, and you have it fail for whatever reason within a larger fuel performance code. I mean, that could be pretty, that could stop your simulation potentially. Or like if it fails to converge and provides inconsistent results to a fuel performance code where that requires those thermodynamic calculations as input, that could mess everything up. So that's why reliability is perhaps the #1 requirement there, in addition to the quality assurance requirements of the nuclear industry. Computational performance is second objective of the development of the software. So again, if you're calling it within, let's say, a fuel performance code 1 billion times, and the Gibbs engine minimizer runs inefficiently, that can have a pretty huge impact on the results and on executing the overall simulation. So that has been a primary area of attention for us, including algorithm development and implementation. And lastly is capabilities. We've expanded the capabilities over the years, where initially the software was aimed at relatively simple regular solution models of a single sublattice, and have since expanded it to include the compound energy formalism with multiple sublattices, ionic liquid model, modified quasi-chemical model, etc. Okay, so to give a bit of an overall image of the input and output operations, here we have the software, and as input, one requires temperature, pressure, element, mass, and a database. And so the temperature and pressure are both, real scalars. The element mass is a vector, and the database is usually in the form of a data file. On output, there's a number of values that can be provided on output, including chemical potentials of the system components, species, phases, all of that. The number of moles of phases predicted to be stable at equilibrium. There's speciation, also the driving forces of metastable phases, and other material properties like heat capacity. This is all pretty similar with all other thermodynamic software. If one wanted to get started with this, you can go to the website, which is given here. And on there's some instructions on downloading the source code, which is managed on GitHub, and building it on Windows, Mac, and Linux. What you will be required is LAPACK to be installed, which is a linear algebra library. That's pretty standard in Mac and Linux, but I think you have to install it separately for Windows. You also need a Fortran compiler, whether it's the GNU compiler or Intel, and you might need to modify the makefile, but Max and our team has done a really nice job cleaning that up, so it can be automated to determine your operating system. And so once you download the code, it's pretty easy to build it, just make. And if you were to build it, I would strongly recommend that you run all of the tests. And that's simply just by typing make tests and then run test to execute them. So we have a software testing tool called Travis that automatically tests Thermochemica on a daily basis. So we have, I think, about 60 or 70 different tests that run every night. So what it does, it'll pull the most recent of Thermochemica and then perform a number of application tests. So what that means is that if there's any changes made to the source code, you can run through all these tests to gain confidence that's producing reproducible results of a number of different types of systems. As far as documentation goes, you can again check this out through the website. There is a user manual and tutorial manual with some example problems to get started. The tutorial manual is still kind of in its earlier stages, but you can get a sense of some problems that'll get you going. We also have included a number of papers that describe both the theory and numerical algorithms that describes how the software works. And for any advanced users, you can also build Doxygen documentation in both HTML and LaTeX format, which can be pretty easy to navigate. But again, that's more for the advanced user. Some current efforts and future plans. So currently we're working on a number of activities. Software quality assurance is an ongoing effort, as it is with all software development projects, although we're going to be really cranking that up pretty soon. So software quality at least in our interpretation, usually means a lot of software testing, and obviously emphasizes some of the fundamentals of software development projects, including version control, automated testing, and documentation. And so again, I'll talk in a minute about some things that will be going on in the coming years. Currently, we're still working on some model capabilities, more specifically the ionic liquid model. So another student, Ben Breeden, developed this capability within Thermochemica to use the ionic liquid model. And that should be released pretty soon, including a suite of verification tests to ensure the numerical correctness of using those models. Also, currently under development is a graphical user interface and various plotting features. So what that means is you can use a GUI much like you do with, let's say, FactSage or Thermocalc, if that's your preferred route, and do things like generate phase diagrams or other types of plots that you can typically perform in other types of thermodynamic software. Now this is, like I said, currently underway, and there are some things we're doing a bit differently than conventional software, and Max has done a pretty nice job with that. One of which is being a bit more transparent and providing the user more control in the way that the phase diagram itself is generated. So that's really to ensure that there's nothing that's missed within the phase diagram generation tool. The other thing, what we're doing is ensuring that that there's consistency in using the same Gibbs energy minimizer for both the equilibrium solve and also for phase diagram development. So that means that all the capabilities are uniform across, and the robust Gibbs energy minimizer is used for both. Lastly, current efforts, we've been working on a lot of multi-physics coupling. So in the past, we've done, that has been mainly focused on BISON applications, which is a nuclear fuel performance code developed primarily at the Idaho National Laboratory in Idaho, United States. So that included LWR fuel, metallic fuel, and trizo fuel. In those examples, what we've done is coupled the two, whereby the thermodynamic calculations provide direct input to solid state diffusion calculations. So Fickian diffusion is not driven so much by chemical concentrations, but rather by chemical potential gradients. But more, currently what we're primarily focusing on in terms of multi-physics coupling is collaborating with the Sandia National Labs MELCOR team for integration to improve sphere accident predictive capabilities. And more apt is coupling with open foam for the SAMOSAFER project. And that's what Nicholas Skuru is working on for his PhD. So what that means is you have a computational fluid dynamics tool that can then call Thermochemica directly to figure out the molten salt chemistry. So that includes phase stability and chemical speciation and the like. The idea there is to make direct use of the JRC molten salt database in those calculations. Some future plans, we'll continue some thermodynamic model development capabilities as they arise, but I would say, like, at this point, it's pretty mature and the needs are not that great. Continued documentation and development of the graphical user interface to make it a more user-friendly experience for most folks. And lastly, software quality assurance will be a major focus in the next year or two, and then most likely after that, by ensuring that we're in closer compliance with more formal standards. So that includes, at least in Canada, the Canadian Standards Association N286.7, specific to analytical software, analytical, scientific, and design computer programs for nuclear power plants, similar to QA requirements in the United States. Okay, so the last major area I'd like to get into are some case studies to give you a bit of a sense of like what you can do with all of this, and I'm hopeful that this gives you a bit of an idea of what can be done. And again, if you wish, you can download the software and do it yourself for whatever application you may have. So it's a pretty simple question here: what can you do with this? And I'd like to share 4 specific case studies. The first is some point calculations. These are pretty typical calculations one would perform with a thermodynamic software tool. Second is simple temperature varying calculations. Again, these are pretty simple, but demonstrating recent capabilities with the graphical user interface. Phase diagrams and graphs. These are, again, relatively new capabilities, but can be very useful for engineers and scientists performing some analyses. And lastly, multi-physics simulations involving molten salts. So the first example that I'm giving here on slide 29 is using the terminal interface. So if you were just doing everything from the terminal, let's say from a Linux computer, this is the type of interface that you can get. This is a relatively simple calculation involving lithium fluoride and uranium trifluoride and uranium tetrafluoride. So in this case here, we have what is predicted. I cut off part of the input just to make it easy to read off the PowerPoint slide. The normal output provides the input parameters at the end. But so in this case, the user can say, hey, I've got this much lithium fluoride, this much uranium, and this much fluorine at this temperature and pressure. And in this case, we're using the JRC database. And then Thermochemical will return this as output and say, okay, we're going to be predicting that we have 74.65 moles of your salt solution and 65.65 moles of some solid solution under this particular example. The output here that is given in this large block is model class specific. So depending on what kind of thermodynamic model you're using, you get a bit of a different output. So in this particular case, what's a little bit more unique to the modified quasi-chemical model, which is what this is it provides as output the quadruplet fractions, which are shown here. So in this case here, remember I was giving a very high-level overview of the modified quasi-chemical model where you're dealing with quadruplets. In this case, the primary sublattice has lithium, U3 and U4 on the primary lattice, and then only fluorine on the second. So here you can see that you have all of those combinations of quadruplets shown here. And then these, again, are the quadruplet fractions. Then we have the solid solution at the bottom, and this appears to be represented by a regular solution model, which is predominantly lithium fluoride with a practically insignificant amount of uranium tetrafluoride dissolved in it. Now, like I said, we're currently in development of a graphical user interface. So this is still very much in the testing stages, but gives a bit of an example of what can be done. So in this case here, instead of dealing with it entirely within the terminal, one can deal with a graphical user interface. And here we're again using this JRC database where the user can provide, can span a series of temperatures. So in this case here, start at a temperature of 300, move to 1,000 degrees, have 10 steps going across it, specify the temperature, specify the pressure and the pressure unit, and then the user can also specify how much of each of the components is included in the calculation. And then on the far right, you have, similar to the terminal output, you can see the output of the predicted phases from this calculation. Not sure if it matters, but this is being developed with Python heavily relying on matplotlib. Case study number 2 considers a much more complicated system of the salt from the JRC database. In this case here, it's looking at prototypic irradiated salt with somewhat realistic composition. And what is happening here is that the temperature is varied across this this composition, and what the plot that's showing here is the predicted number of moles of different phases as the temperature increases. So we're starting here at about 300 degrees Kelvin. So it's pretty, basically room temperature. Obviously not quite realistic, but and as it's heated up, you can see that initially you basically only have some solid phases formed, and some molten salt starts to form at at low temperatures, but at nominally 600 or so Kelvin, everything melts, and you have a predominant melt region right up here, up to a point where vaporization takes place. Again, this should be considered as a demonstration example, but right around 1600 degrees K for this particular example, you start getting vaporization where you can see the liquid salt becoming now gaseous. Again, this is just intended to demonstrate some capabilities. Case study number 3 is we're considering here some phase diagrams. I specifically chose some examples that can be directly compared to FactSage, just so you can see that everything's working just fine. In this case here, we're looking at the lithium fluoride, cesium fluoride phase diagram. Where on the left is the work from Elisa Capelli of the lithium fluoride, cesium fluoride system, and then the right is the calculation with Thermochemica of the same system. Similarly, one can compute gaseous partial pressures, which can be pretty handy looking at vapor pressures of certain components of your system. So again, on the left, we're looking at the vapor pressures of lithium fluoride, cesium fluoride, and thorium tetrafluoride from Elisa Capelli's model, and you can also see how there's experimental data points superimposed on here to emphasize that these models are very much empirical, right? And then the figure on the right shows the comparable phase diagram that was computed by Thermochemica. So if you want, you can perform those types of calculations. Now looking at something a little bit more sophisticated, or at least more current, I'm about to show an animation of a demonstration problem that was presented last week by Nicholas Skuru to the SAMOSAFER committee, and I'd like to emphasize that this should be viewed as a demonstration problem, not as a real engineering problem. At least at this point, this is mainly intended to demonstrate progress. But what you're about to see is one-way coupling of open foam with Thermochemica to look at behavior inside of a molten salt reactor. So open foam, again, is a computational fluid dynamics tool that is typically used to look at things like heat and mass transfer, single and multi-phase flow, and the like. And for this particular example, we're looking at lithium fluoride with cesium fluoride. And so what you're going to see in this, again, demonstration problem, it's going to be a square where we're going to be fixing the temperature on all corners of the square, where the left and bottom edges are at a relatively low temperature. The top and the right edges are at a high temperature. And so initially, open foam is calculating time-dependent heat transfer within this domain, and it provides the temperature directly to Thermochemica, which then predicts the salt chemistry. And this is again using the same system I showed on the last slide from Elisa Capelli of the lithium fluoride, cesium fluoride system. So you'll see the temperature on the top left, the phase fraction on the top right, and the cesium fluoride partial pressure on the bottom left. So in this example here, you're seeing this animation. So again, temperature here on the top right here. There, I'll do phi. Whoops, not very clean, sorry. And then partial pressure over here. Now the XY plot that's shown on the bottom right, if you were to take a line that goes directly, kitty corner from bottom left to top right, it plots the fraction of the partial pressure, I think, of cesium fluoride. So you can, I'll just play it one last time. So you can see here that we're starting to make progress in this type of coupling, and eventually this computational capability will be open source in case you have that for other applications. Obviously, the capabilities here are very early stages, but the intent here is that we can eventually look at all sorts of other matters related to heat mass transport coupled with thermodynamics, like precipitation, severe off-gassing, local changes in salt chemistry, and how that affects other parts of reactor behavior. Okay, so I have about 5 more minutes for my presentation. I'd like to end off with a few best practices and additional information. And this first one, I'd like to share a word of caution, and this is not specific to thermochemical, but really any thermodynamic equilibrium software, just to be conscientious of it. And the reason why I'm bringing it up here is just because it is more prevalent with these molten salt systems. So imagine, you may recall at the beginning of the lecture, I gave an example of how the molar Gibbs energy plots can be a graphical interpretation of your equilibrium state. So more specifically, if one were to draw the lowest common tangent, between phases, whereby the system composition is in between them, you can use that as a graphical interpretation of what phases will be stable at equilibrium. So here on slide 37, I have an arbitrary system, AB, and it consists of one solution phase alpha, and it also consists of 3 stoichiometric phases. We got pure A as a solid, we got pure B as a solid. Here, I'll just highlight in case you can't see my cursor moving. So there's pure A, pure B, there's solution phase alpha, and then there's also a stoichiometric phase A2, B3. And if the system composition is shown here in this vertical dashed line, one can use this lowest common tangent to graphically interpret the equilibrium state here. And you can see that if you draw a tangent between this alpha and A2, B3 phase, the system compositions are in between, right? Nothing special here. This is all very rudimentary. Now, what's worth noting is, let's say we consider another scenario of this exact same system, but where the system composition is exactly in line with A2B3. And so in this case here, if we have exactly, let's say, 2 moles of A and 3 moles of B, we have, how do you draw a tangent line here? So, you can draw a tangent line between alpha and A2B3. You can also draw a tangent line between A2B3 and B0, the B solid, where you have 0 moles of B or 0 moles of alpha. Who's to say either one is more appropriate? Now, the important thing to note here is you can't define a line by a single point. Mathematically speaking, that's called underdetermined. And what does it practically mean? Well, the system really, one should redefine the system components. It shouldn't be A and B in this case. Instead, it should be A2, B3. What does it practically mean? Well, the chemical potentials, which are normally defined by this lowest common tangent line, are now meaningless if you, again, define them by A and B. Okay, so you can relate this idea to many other thermodynamic systems. What's worth noting, though, is that, as I mentioned a minute ago, I bring this up because it's more prevalent with these salts. And the reason why is because the species in these salts are never, at least using the modified quasi-chemical model, they're not the pure elements. Instead, you always have an integer combination of elements. For example, lithium fluoride, beryllium difluoride. And so in this case here, I have a ternary plot that represents lithium, fluorine, and beryllium at the corners. But if you're looking at only the salt, then that's really represented by, again, you're looking at pairs here: lithium fluoride, lithium fluoride, lithium fluoride, beryllium difluoride, and beryllium difluoride, beryllium difluoride. In this case, you have a 3-element system, right? So you need at least 3 points to define a 3-dimensional plane. Well, here we have 3 points, but they're collinear. So it's the same idea as trying to define a line, like 2-dimensional space by a single point. It's underdetermined. So why is that important? Well, if you have a calculation here where you're predicting that only the molten salt is predicted to be stable, in other words, you're in 3-dimensional space, but you're trying to define it by this line, it means that the fluorine potential is really meaningless. similarly, the element potential lithium and beryllium are also meaningless. Now, if you run this with some software, there'll be cases where you'll get some values, but again, consider them meaningless. But it's not always the case. Like, for example, if you had this molten salt predicted to be stable with another phase for this particular example, then you have basically 3 points in a collinear line and then something else. So you can uniquely define a plane in 3-dimensional space. But anyways, just wanted to express a word of caution if you're performing any of these types of calculations. So now to start wrapping up the presentation, if anyone is interested in some additional information, specific, let's say to CalFAD, there's some excellent resources out there. I'm not trying to be exclusive, but two I think that are worth noting are one from Art Pelton called Phase Diagrams and Thermodynamic Modeling of Solutions, and also another one from Mats Hillert, Phase Equilibria of Phase Diagrams and Phase Transformations. Specific to the modified quasi-chemical model, there's a series of 4 articles that outline the development of this model from Art Pelton and also Patrice Chartrand from Montreal. Very nice pieces of work. More recently, Max Poschmann had a paper from CalFAD. Max did a lot of the development at Thermochemica with salts, and he gives a full derivation of the model there. So to summarize, these computational thermodynamic tools can be used to predict various aspects of molten salt chemistry, including speciation, precipitation, and off-gassing. Thermochemica has been used for multiple molten salt applications using the JRC database. Again, I'd like to emphasize, there's many other software tools out there that are very good. FactSage and ThermoCalc are 2 excellent pieces of software. I'm not trying to exclude them, but again, just because we're using Thermochemica for this particular project, that's why the focus of this presentation has been on that software. It's free to use if you want to use it, but note that the JRC database is restricted. So if you want to, download the software, it's up to you. Check out the website, and please don't hesitate to reach out if you have any questions. Looks like we're good for time, Stefano, and thank you everyone for your attention.